Hello and welcome at Vision Components. Today I would like to take you with me onto a journey over the past decades, roughly starting in the early 90s, to show you the evolution in the hardware of embedded vision systems, mainly having a closer look on 2 points. It's the size, it's the title of today, so miniaturization in embedded vision systems, but also a second look onto the computational power. To start this, we are going to build up our reference, not in size, but in computational power, to start with the computational power of 1, just to have a reference. This reference, something that looks from today's point of view quite bulky. This is a vision system of the early 90s, and we put this as reference computational power 1. Then, before I go through the different steps, you will see more or less what can be done today. This is something that has been developed very recently, and this small little thing contains everything that you need to build up an embedded vision system. So now let's have a look at the evolution from this bulky box, from our reference 1 up to today. To do this, we will bring up a small timeline and we will try to go through this over the next minutes until we reach to, let's say, the recent years to go into more details of the latest product. So as said, we start in the 90s. And yes, I was already born. The box contained a Motorola 68000 processor. And as we said, this is reference 1. So it had 1 MIPS of computational performance. Then it was 1995, 1996, when Michael Engel presented the first industrial smart camera, the VC11. This was based on a DSP, so a digital signal processor from analog devices. And this chip had, compared to our reference, higher computational power by a factor of 40. At the same time, being much smaller than the bulky box that we have seen earlier as the reference. Then we stay with the form factor. We come to roughly the year 2000. Then we switched to a DSP from the company Texas Instruments, which in comparison to our reference had now a computational power of 1200. So the jump in computational power was huge while keeping still the compact form factor. Then we had several evolutions in these DSPs, steadily having an increase in computational performance. So we can then go to the year roughly 2005. We had the gigahertz processing units from Texas Instruments reaching a computational power of 8000 compared with the reference. The next step was in the year 2014 when there was a complete change in technology, when we left the digital signal processors and went to the ARM processors, which we had seen coming more or less from the consumer area. So we can really say there's an impact in the machine vision sector, in the industrial sector from the consumer area. And this happened starting in the year 2013, 14, 15. Then we made the switch to an ARM-based processing unit in 2014. So this processor is a so-called system on chip, an SoC, from the company Xilinx. At the beginning, we only used for image processing the ARM processing unit, so the CPU. And if you only have a look at the CPU, the computational power here is about 15,000. So it's a jump, a factor of 2 from the last camera based on the DSP from TI. Then it took some time to also take advantage of the FPGA that is inside the processing unit. So as I said, it's a system on chip based on 2 processing units, CPU, dual core ARM, and an FPGA. Now the FPGA, if you take this into account, this can speed up applications to a factor up of 20. So this is a huge jump without changing anything in the size, because it's still the same hardware. You can just use more out of the performance of the hardware by implementing FPGA blocks into the final product to have a real jump and increase in computational power. Then in 2019, we added a second ARM-based processor. This was from Qualcomm. It's the Snapdragon 410. No FPGA, so it's a pure CPU-based solution with, again, roughly a gain of a factor of 3 in performance compared to the Zinc from Xilinx. Then in 2020, that was, let's say, the biggest jump, not in performance, but the biggest jump in size. This is based on a very compact processing solution. It's also based on a small FPGA and a small processing ARM-based unit to really reach an extremely small form factor, which we are going to have a closer look at in a couple of minutes. The latest development, this is again quite a huge jump in computational performance. It's the VC Power SoM. So this has been presented this year and will be available on the market early next year. This is a very powerful FPGA board, a very tiny board with a very powerful FPGA that can be combined with any CPU, which offers a MIPI interface. So we are going to get a bit in more details also later. Now we had a look on what happened over the past decades, and now I would like to go a bit in more details of what we have right now on the market and the capabilities, the possibilities of the different solutions. To give you an idea about the performance, which I was just talking about, I would like to show you one real-life application example based on this Zynq, so the SoC, and taking advantage of these two processing units, the ARM and the FPGA core. If we look at the solution, this is a 360-degree scanning device to detect and scan 1D barcodes, mainly in retail applications. So you can imagine you can more or less throw objects through this 360-degree omnidirectional scanner. These objects can go through at a speed of up to 2.5 meters per second. And while this is happening, all these 6 cameras, they have to find the barcode in the image and then they have to read the barcode. So the barcode can be maybe only seen in half by one camera and then the other half in the other camera. So they have to communicate, they have to stick the barcodes together to just output one single read of the barcode which is on the product. And this is only possible by the use of the FPGA in parallel with the ARM processor. All these cameras in total are producing about 1200 images a second. And all of these images are processed or have to be processed in real time while this object is passing through, let's say, the scanning area of these 6 cameras. Another typical application for this processing performance is something like this. It's a triangulation or a profile sensor based on a laser line. And this can run up to 4 kilohertz and really doing all these 3D inspection tasks and generating the 3D point cloud. So this is something we've seen already extremely compact. This technology started 2014-15, a couple of years ago. Then our goal is always, of course, to push the evolution of embedded vision systems, and this led us to 2 very recent products. The one we've seen earlier is the VC picoSmart, where you have everything. Again, I will show it once more. That's what we have seen earlier. It has really the size of a camera module, but on this board, as you can see here, we have everything. We have the image sensor, we have onboard memory, we have, again, 2 processing units. You have 1 ARM core and 1 FPGA, both to do the image processing and the communication with the outside world. And of course, yes, you need the connection, the physical connection, to get the processed data information out of this. And this is meant to be a very powerful, ultra compact vision system to build up vision sensors which are really dedicated to one specific task. So this allows you to very quickly generate a vision sensor, typically a vision sensor that has one task. It can be an object sensor, it can be a color sensor, it could also be a barcode reading device, quality checking sensor for different very vertical markets. This tiny little board is a fully featured, complete embedded vision system with a computational power of 4,000 times the computational power of our reference bulky box that we've seen earlier, plus the speed increase of the FPGA that is on board. This is, I think, the best way to show the evolution and the development that the embedded vision technology or the embedded vision market has made over the past decades, is that now you have 4,000 times the computational performance on a fraction of space that is needed compared to what we had in the 90s. So this is, for us right now, we don't see any smaller embedded vision system on the market. So this is the smallest you can do today if you would like to build up your embedded vision solution, of course, based on industrial components. So I'm not talking purely consumer products, because of course you could find maybe a smaller image sensor, but based on long-term available components, industrial components, this is really the smallest you can go today, right now. So now we've seen what can be the smallest of the smallest you can do. Then we can have another look onto the computational power. Also, one of the latest developments is another very tiny board, but with a quite huge FPGA that is on this board. And this board allows a multiple MIPI input. All these image data which comes over the MIPI interface can be processed in this FPGA. Just to give you a reference, so we've seen earlier the solution based on the SoC from Xilinx, which also has an FPGA part in the chip. This FPGA here has about 5 times the performance of the FPGA, which we've seen earlier with the application showing the barcode scanning device. So this FPGA is a performance of 5 times of the one we've seen earlier, allows a direct MIPI input and then to process all this data in the FPGA, and then you can output the results of the processed image data, and this output again will be outputted over a MIPI interface. So that means that you can have huge image pre-processing and processing on this tiny little add-on module. It's a system on module, and then you can output this again over MIPI to connect this to any CPU solution, another SoM or your own CPU board. So now we had a look onto the evolution that we went through over the past decades, more or less over the past 3 decades. And what we've seen is that the development cycles are getting shorter and shorter, or you can also name it, the development is going on faster and faster. At the beginning, it took years before getting new processor series, processor families, to really have an increase in computational power or to getting to a smaller form factor. We've seen there's a big influence from the consumer industry, and then of course mainly the technology that is coming out of the consumer industry that started for us roughly about 2014, 2015, 2016. And this influence mainly comes from the consumer industry, and they are from products, of course, from the mobile phones and the tablets. A mobile phone is a very compact embedded vision system. You have a lot of camera sensors in it. You have a lot of processing units, also different type of processing units in mobile phones and tablets. And this influence is getting bigger and bigger because, of course, there's much more money to do development on the consumer side. And now the industrial applications of the industrial world or the industrial machine vision applications, they are influenced by the developments that are done on the technology used for the consumer market. So at the end, so the title was Miniaturization and how to build up your perfect embedded vision system. The final choice, if you go with a homogeneous system only using a CPU, or a heterogeneous system using different prototypes together. So this choice is mainly based on your final application. So this is the point where you can get in contact with us. This is what we're doing now for about 25 years, is to determine and to choose the right components for your specific solution, your specific needs. So if you have an embedded vision application, an embedded vision project, please do not hesitate to get in touch with us, and then we can go much more into details, which would be the best fit of components for your application. So thank you very much for your attention. If you have any questions, do not hesitate to get in touch with us. We are happy to answer all your questions and of course to find the right solution to your project. Thank you very much. See you next time. Bye bye.